Every person in the world once asked themselves, how did the universe begin? Some of our ancestors considered that it dated approximately 5000 BC. Of course, archaeological findings prove this suggestion wrong, as only Earth formed 4.5 billion years ago. Greek philosophers believed that the universe existed for an infinite amount of time and would last forever. Astronomer Edwin Hubble made one of the most remarkable discoveries in the field in 1929. He noticed that galaxies move in the opposite direction from us, implying that the universe expands. Moreover, scientists suggested that they accumulated in one place back then, which brought us to the development of the Big Bang cosmological model. There are, however, more popular theories, like Isaac Newton's theory of gravity and Albert Einstein's general theory of relativity. Nowadays, scientists apply both of them to interpret the world. While Einstein's approach characterizes the universe on the macro scale, quantum mechanics apply to a micro level. Yet, these two theories contradict each other. One of the crucial tasks for Stephen Hawking was to find a way to combine both sets of principles. His search started with the analysis of space and time models. Join this expedition into the universe. Hawking has described how the latter looks, why objects act in certain ways, and how physics developed over time. While exploring these topics, you will realize the power of human intellect and the world's complexity. Physics is a highly counterintuitive field. So get ready to be astonished. Sky, red, universe, is the limit. Einstein's legendary equation E=mc² demonstrated that the more energy the object receives while moving, the more mass it will gain. Therefore, it cannot increase its speed at some point due to elevated mass. Other Einstein's revolutionary findings indicated that the time-space continuum is warped, so light does not move straight. Its direction can be changed by massive objects causing its deflection. Imagine dropping a stone in the sand. It will create an indentation. Now you may shine a torch into the rock, you will see how the light bends into the dint. It does the same in space, curving due to the planet's weight. Consequently, massive objects also slow down time flow. This effect rests on the principle that lesser light energy leads to its lower frequency, that happens when it needs to move up against gravity. Recall the cases when you spend a vacation in the high mountains. Did you feel that time flies? It's not only because you were on holiday. Minutes ticked away faster there. In 1962, an experiment proved it. Scientists put one clock at the bottom of the water tower and another at its top. As a result, the device placed higher ran faster. This principle is fundamental for the work of new navigation systems. If they disregard it, the signals from satellites wouldn't be so correct. What about the perception of color? We distinguish between hues because they have diverse wavelengths. Long waves are seen as the red part of the color spectrum, while short ones are in the blue segment. Using this knowledge, we can observe the expansion of the universe. Look what I found on the Headway app. Eyes. American astronomer Edwin Hubble estimated that almost all the galaxies around us are in the red part of the spectrum, meaning they are moving away. This conclusion rests on the Doppler effect. It states that the wave's frequency increases as the source and observer move toward each other and vice versa. For example, to estimate a car's speed, police use specific devices that calculate the length of radio waves emitted by the vehicle passing by. Fortune tellers are liars. Alexander Friedman, a Soviet physicist, has predicted that the universe looks almost the same in any direction, which Penzias and Wilson later proved. These two American physicists discovered that a specific microwave noise was coming from outside our galaxy. This finding means that we receive light from the farthest parts of the cosmos, which reaches us now because of the universe's expansion. Besides, scientists concluded that, most likely, the latter will never cease because there isn't enough gravity to influence the movement of an enormous mass of all objects in space. Max Planck, a theoretical physicist, suggested that different waves only emit a specific amount of energy that increases with their frequency. This assumption became the foundation for Heisenberg's uncertainty principle. It states that it's impossible to predict a particle's position and speed exactly. To find the former, we need to illuminate, for instance, the electron so that it reflects the light. However, the latter's wavelength affects the particle's speed. The shorter it is, the higher energy it contributes to the electron. Therefore, we won't know its speed and position simultaneously and never determine its future location. This discovery demonstrated that our world could not be deterministic. Heisenberg's findings also suggested that particles can behave as waves. A two-slit experiment proved it. Imagine directing a wave of water on a board with two closely spaced slits and a piece of paper behind. After passing the board, it will leave a long mark on the sheet, showing that it passed through both slits since waves expand while moving. Now imagine that you have to drop a water droplet through one of the slits. The mark on the paper will show only one wet spot. But that's not how quantum mechanics works. Even if the researcher shoots only one electron towards the partition with two slits and the screen behind, the latter will show that the particle behaved as a wave. Notably, it crossed both slits simultaneously. This discovery was essential for explaining the atom's structure. Scientists used to believe it resembled the solar system. Electrons orbit around a central nucleus. Yet this model contained a flaw. It meant that particles would lose energy. The solution was to consider electrons' moves as waves. There are parts even smaller than atoms. Gell-Mann's proof that protons and neutrons are not the smallest particles was revolutionary. By making them collide, he found out that they consisted of quarks. Scientists divide them into 6 categories: top-down, up, charmed, strange, bottom. Protons and neutrons comprise 3 quarks each. Even more exciting, each particle has its antipode. For instance, an electron's one is called a positron. Yet the meeting of opposites results in destruction. Thus, we may suppose that anti-we, created from antiparticles, exist somewhere on Earth. Yet we should never touch them as they will turn us into a flash of light. A prognosis states that a proton can turn into an anti-electron. This transformation occurs if one of the 3 quarks inside the former gains more energy to become the latter. Yet it happens incredibly rarely, once in 1 followed by 30 years. We also know that galaxies consisting of quarks and antiquarks cannot exist. These particles would annihilate, leaving considerable radiation we could have detected. It is fascinating why we now have more quarks than antiquarks in the universe. How did this happen? Even if their proportions were the same initially, it would still lead to this dominance. Why? High temperatures initially empowered quarks, antiquarks, anti-electrons, and electrons with colossal energy, allowing their transformation. Yet the physics laws affect various types of particles differently. According to them, the universe's development influenced more anti-electrons, causing them to change into quarks. This inequality has benefited us enormously. Without it, opposites would destroy themselves, and instead of matter, we would have only radiation. It means the cosmos had no stars, Earth, or humanity. Now let's consider the appearance of black holes. They do not randomly occur at some moment in space. When a star ages, it begins to condense, therefore, its gravitational force grows. Finally, the gravitational field increases to the point when the light cannot escape at all. If the fastest mover in the universe can't do it, nothing else will get away. Thus, a black hole appears. The circle of light around it is called the event hole. Black holes not only catch but lose, too. At some point in examining the black holes, Hawking concluded that they emit radiation like any hot object in the universe. Yet, how is it possible that even light cannot escape their boundaries? As it turned out, radiation appears not inside the black hole but in the area outside the event's horizon. It contains so-called virtual particles, which our devices cannot detect. After entering a black hole, they can drop out of its area as antiparticles or real particles. This finding means that there is a way out of a black hole. For example, if a person enters it, its mass will increase. Then, this addition returns to space as radiation, in which human particles transform. As for the universe's formation based on the Big Bang theory, after the universe's temperature fell and equaled that inside the stars, neutrons and protons started to combine into nuclei. The first ones created were deuterium, which formed helium and other elements. George Gamow, a theoretical physicist, and his student Ralph Alpher, a cosmologist, described this process. As witty as he was, Gamow convinced another scientist, Hans Bethe, a nuclear physicist who didn't participate in writing this work, in adding his name to the article. The combination of their last names, Alpher, Bethe, and Gamow, reflected the alphabet letters alpha, beta, and gamma. They predicted Penzias and Wilson's finding of radiation from the furthest reaches of the universe. Early formed chemical elements made the first stars. When they exploded, their wreckage scattered over the universe, creating planets and other astronomical objects. Alan Guth, an American theoretical physicist, supposed that cosmos initially developed at an unthinkable rate. Imagine 1 followed by 30 zeros. That's how the space extended in less than a second. Its temperature was scorching, and protons, neutrons, etc., quickly moved in different directions. While developing, the universe became cooler, and particles' energy decreased. Did you know? Scientist Jeff Steinhauer and his colleagues created a mini version of a black hole on Earth in 2009. The possibility of time travel. At some point in your life, you might wonder, can we turn back time and ensure the objects get into their previous form? According to the second law of thermodynamics, entropy grows over time. Simply put, the latter means a disordered condition, some randomness. For instance, breaking a cup moves it to entropy from the past state of order. But you cannot unbreak it. We can divide time into 3 arrows or directions. One is entropy, another is our perception of time, and the last is the universe's expansion. The number of chaotic configurations in the cosmos is much bigger than ordered ones. The analogy with a cup will explain this better. We can break it differently, for example, its handle or the bottom will fall out. Yet, there is only one chance for it to stay in order, if we don't damage it. Science fiction writers enjoy fantasizing about navigating galaxies. They suppose that people will someday figure out how to move faster than the speed of light. In reality, space tourists will feel they spent little time out there compared to those who wait on Earth. They will likely come back a bit older just to discover that all their friends died many years ago. However, if such travelers could bend spacetime to connect 2 points in space, they would create a wormhole. It would allow us to reach Alpha Centauri as if it was just as close as the Moon is to Earth. Moreover, the wormhole's existence would also allow time travel. The structure of spacetime was also a focal point of string theories. It analyzes one-dimensional extended entities, smaller than atoms, electrons, or quarks, and calls them strings. They can be open and closed. If 2 closed ones unite, they will form something similar to a pair of trousers. They interact with different forces, which causes their fluctuations. However, these theories have a vital condition: such strings can only exist if there are 10 or 26 dimensions. We have only discovered 4 so far, but researchers believe others are visible on tiny scales. Thus, we cannot detect them at the moment. Nevertheless, we won't be able to travel through these dimensions since they are too small. Why is string theory so important? Strings gained little popularity at first. However, in 1984, researchers began to scrutinize them. While working on the supergravity theory as a part of string 1, they realized they couldn't prove that it was finite yet. They also discovered that strings could clarify the reasons for specific particles' existence, so they based a heterotic theory on them. The new one could interpret different particles that scientists examine. Since it only worked for tiny scales, researchers must continue searching to develop a more consistent theory. But why are they so interested in this incompatible with reality set of principles anyway? The existence of additional dimensions allows us to get around the limits of general relativity, which state that we cannot move back in time and faster than light. String theory tolerates an alternative route through other dimensions. Imagine a figure similar to a donut but flat because it exists in a universe with only length and width. You are on the right side of the pastry's inner circle. How do you get to the left side? Since you are also two-dimensional, you will have to follow a trajectory similar to an arc. But if you had a third dimension, you could jump straight to the left side. String theory aims to provide us with the shortest possible route through space. Hawking suggested that the universe's dimensions were all curved initially. However, our four ones became flat, probably due to an anthropic principle. For living creatures to develop, a two-dimensional universe wouldn't be convenient enough. They would have to move each other up to get where they needed to go. Besides, they couldn't eat because the gastrointestinal tract would simply divide them into parts. Planets and stars won't be possible either. Gravitational force in a two-dimensional cosmos will not allow the sun to exist due to gravitational pressure. It would likely turn into a black hole, meaning that life on Earth wouldn't even have a chance to begin. On a smaller scale, the situation won't be good either. Electrons won't orbit the protons due to gravitational pressure. They would likely fall apart, so we wouldn't know atoms as they are in a four-dimensional world. Conclusion. As you can see, everything is ambiguous in the universe. Scientists try to connect all the dots regarding our discoveries about the world to see how it really looks. However, the more we find, the more questions arise. Why do quants behave weirdly? We have much to explore, but isn't it an incredible journey? Hawking spent a significant part of his life examining black holes. First, he thought they could not emit anything because of enormous gravitation, which trapped everything inside. Later, he realized that some particles could leave a black hole. Physics is a magical science that makes you question everything you find. It is all about uncertainty. Usually, we are shocked when people say that they have figured out everything about themselves and their future. And we feel insecure about ourselves. What is wrong with me? Why can't I understand what I need in my life? Don't worry about these feelings. These are quants that bring uncertainty into our lives. Unpredictability is the universe itself. People who are now sure about something were or will be utterly unsettled about something else in their past or future.